Lesson 1.4, Inverses of Functions. Essential question, what is an inverse function and how do you know it's an inverse function? Understanding inverses of functions. Recall that a relation is any pairing of the elements of one set, the domain, with elements of the second set, the range. The elements of the domain are called inputs, while the elements of the range are called outputs. A function is a special type of relation that pairs every input with exactly one output. In a one-to-one function, no output is ever used more than once in the function's pairing. In a many-to-one function, at least one output is used more than once. An inverse relation reverses the pairings of a relation. If a relation pairs an input x with an output y, then the inverse relation pairs an input y with an output x. The inverse of a function may or may not be another function. If the inverse of a function f of x is also a function, it is called the inverse function and is written the inverse of f of x. If the inverse of a function is not a function, then it is simply an inverse relation. A. The mapping diagram shows a function and its inverse. Complete the diagram for the inverse of the function. Is the function one-to-one or many-to-one? Explain. -4 becomes -2, so -2 becomes -4. 0 becomes -3, so -3 becomes 0. 1 becomes 2, so 2 becomes 1, and 4 becomes 1, so 1 becomes 4. The function is one-to-one. Is 1, 2, 1, because no output is ever used more than once. In the functions pairing. Make that look, there we go, that looks like me. Is the inverse of the function also a function? Yes. Yes, it is. Why? Because for each input, there is only one output. That looks only one output. There we go. B, the mapping diagram show a function and its inverse. Complete the diagram for the inverse of the function. Is the function, the question will be, is the function one-to-one or many-to-one? So -4 becomes -2, then -2 becomes -4. 0 becomes -3, so -3 becomes 0. 1 becomes 2, so 2 becomes 1. 4 becomes 2, so 2 becomes 4. This function is many-to-one. Is many-to-one, because there are two inputs. That would be 1 and 4 right here. Two inputs these two right here, and they group with that 2. Two inputs, 1 and 4, that have the same output. Please don't let your English teacher see this because my grammar is not exactly perfect. Is the inverse of the function also a function? No, it is not. No. Because the input 2, has 2 different outputs. I better spell that out. 2 different outputs. And those would be, let's do this in different color, 1 and 4. And we're talking about right here. Okay? So this is a function. This is not a function. C, the graph of the original function in step A is shown. Note that the graph also shows the dashed line y equals x. Write the inverse of the function as a set of ordered pairs and graph them. Function -4, -2, that's right here. It's already graphed. 0, -3 is right there. 1, 2 is right here. And 4, 1 is right there. So the inverse of the function, so -4, -2, that becomes -2, -4. So let's find -2, -4 is right there. Okay. And then 0, -3 becomes -3, 0. -3, 0 is right there. 1, 2 becomes 2, 1. 1, 2, 1. And then 4, 1 becomes 1, 4. So 1, 4 would be right there. Okay? So this point is the inverse of that point. That point is the inverse of that point. And there we go. And there we go. Okay. Notice that they are the same distance from this y equals x line. So in math terms, we say the graphs are reflections across the line y equals x, which makes sense because ordered pairs in a function and its inverse have their x and y coordinates reversed. Let me show you. You got x, y, x, y becomes y, x. Okay. The composition of two functions, f of x and g of x, written f of g of x, and read as f of g of x, is a new function that uses the output of g of x as the input of f of x. For example, consider the functions f and g with the following rules. F, add 1 to an input. G, double an input. Notice that g of 1 equals 2 times 1, which is 2. So f of g of 1 equals f of 2, which is 2 plus 1, and that equals 3. You can also find that g of f of x. Notice that f of 1 equals 1 plus 1, which is 2. So g of f of 1 equals g of 2, which is 2 times 2, which equals 4. For these two functions, you can see that f of g of 1 is not equal to g of f of 1. You can compose a function and its inverse. For instance, the mapping diagram illustrates that the inverse of f of x, where f of x is the original function from step A, and the inverse of f of x is its inverse. Notice that the range of f of x serves as the domain of the inverse of f of x. Complete the diagram. What do you notice about the outputs of the inverse of f of x? Explain why this makes sense. So negative 4 becomes negative 2, then negative 2 becomes negative 4. 0 becomes negative 3, so negative 3 becomes 0. 1 becomes 2, so 2 becomes 1. 4 becomes 1, so 1 becomes 4. The outputs of the inverse of f of x exactly match the inputs of the inverse of f of x, that is, if the, that is, do this right here, let's see, the inverse of f of x equals x. The function takes each input and assigns it to an output the inverse the inverse takes that output as an input and assigns it back to the original function input. Basically what I'm saying is x, y becomes y, x. And this would be f of x, and that would be the inverse of f of x. So the composition takes an input, assigns it to an output, and then assigns it back to the original input. That'll get it. It's kind of hard to understand first, but just bear with me, and by the time we finish the lesson, you'll know exactly what I'm talking about. What is the relationship between the domain and range of a relation and its inverse? See, the range of the original relation is the domain of the inverse relation. And the range of the inverse relation is the domain of the original relation. In step D, you saw that for the inverse function, inverse of f of x equals x. What do you expect f of the inverse of f of x to equal? Explain. It should also equal x. It should also equal x. The function inverse of f of x maps the output of f of x back to its input. So f of the inverse of f of x will then map that input back to the input of the inverse of f of x. I know it sounds a little confusing, but when you work with it some, it'll get a bit easier. Finding the inverse of a linear function. Every linear function f of x equals mx plus b, where m is not equal to 0 is a one-to-one function. So its inverse is also a function. To find the inverse function, use the fact that the inverse functions undo each other's pairing. To find the inverse of a function f of x, follow these 4 steps. Substitute y for f of x, solve for x in terms of y, switch x and y, since the inverse switches inputs and outputs, replace y with the inverse of f of x. To check your work and verify that the functions are inverse, show that f of the inverse of f of x equals x, and that the inverse of f of x equals x. Wow, that's a tongue full, isn't it? Find the inverse function of f of x for the given function f of x. Use composition to verify that the functions are inverses. Then graph the function and its inverse. So I'll let you go through A. Go ahead and stop it and go through A and follow it the best you can. When you get back, we'll do B together. I'm glad you're back. So B, f of x equals 2x minus 2. So step one, we're going to let y replace f of x with y. So we got y equals 2x minus 2. Well, we're going to start undoing that. First, well, let's add 2 to both sides. So we got y plus 2 equals 2x. And then we're going to divide both sides by 2. So we got y plus 2 over 2 equals x. Now we're going to interchange x and y. So we'll put the y where the x is and x where the y is. So we got y equals x plus 2 over 2. Replace y with the inverse of f of x. So with the symbol, inverse of f of x equals x plus 2. Now let's go ahead and graph those real quick. We will make this in red here. So let's find negative 2. 1, 2. All right, and the slope is 2, so we'll go up 2 and right 1, up 2 and right 1, up 2 and right 1. Down 2 and left 1. There we go. Let's see if I can draw a straight line and connect them. Is that going to do it? It's a little off. And that gets it right there. All right. So that is f of x. F of x. Now let's graph the inverse of f of x. So first, I think what I need to do, if the inverse of f of x equals x plus 2 over 2, I'm going to put this in slope-intercept form. And let's see, that's 1x divided by 2 would be 1/2 x, and then 2 divided by 2 would be 1. So let's find 1 here. And let's see here. We're going to go down 1, right 2. Well, let's see. 1, up 1 and right 2. Up 1 and right 2. And let's go down 1 and left 2. Down 1 and left 2. And draw us a line. I want you to notice something. See if you notice it. What do you notice? You notice that they both cross the y equals x line at the same point. They both cross the y equals x line at the same point. That's significant. Verify that the inverse of f of x equals x, and that f of the inverse of f of x equals x. So let's do the inverse of f of x. Well, what is f of x? F of x is 2x minus 2. So we're going to put 2x minus 2. All right. Now we're going to substitute that in for x. So, and then we put 2 here. Let me do that in blue, because that is the inverse of f of x. All right, good. Now what can we do here? Negative 2x plus 2x, those are going to cancel out, and we're left with 2x over 2. The 2's cancel out, and you're left with x. So that worked. Now let's try the other. So we have f of the inverse of f of x. Well, what is the inverse of f of x? That is x plus 2 over 2. So we're going to put that in for x. We'll put that in for the x right there. And so this is minus 2. And what can we get rid of? Well, we can get rid of this. Those 2 cancel out, and we're left with x plus 2 minus 2. Well, those will cancel out, and you're left with just x. So that worked out. That worked out. 3. What is the significance of the point where the graph of a linear function and its inverse intersect? Well, let's see here. Let me roll that up a little bit. Not that's going to matter. The lines intersect on the line y equals x. They always intersect there. The lines intersect on the line y equals x, which is where the value of the function and its inverse are the same. Number 4, the graph of the constant function f of x equals c for any constant c is a horizontal line through the point 0, c. Does a constant function have an inverse? Well, yes, it has an inverse. Let's take a look so that you understand what a constant function is. So here's your x, or here's your y. Here's your y. And here's your x. All right, and let's see. So 0c, let's find some point, and we'll just say right here. This is c. The constant function looks like this. And there it is. There it is. It goes through whatever that, and that could be 1, 2, 5, a million, whatever. So there's your constant function. Does the constant function have an inverse? Well, sure, because you have 0c. Could you not make that, the inverse would be c, the inverse would be c0. So that would be any point here on the x-axis, and we'll say that's right there. Or it could be on the left side or either way. And so there that goes. That's going to look like that, and we draw it down like that. And maybe that's all right. There it is. Does it have an inverse? Yes. Does it have an inverse function? Does it have an inverse? Yes. Does it have an inverse function? No. Why? And that would be because a constant function assigns every input to the same output. It is a many to one function and its inverse is not a function. All right, and we'll pretend like this one here is, we'll say this is y equals 1. All right, so y equals 1. So what does that mean? Well, let's see. If we map that, what that means is What that means is let's see here. Let me say that for class. I better explain that in class. Find the inverse of f of x for a given function f of x. Use composition to verify that the functions are inverses. Then graph the function and its inverse. So f of x equals negative 2x plus 3. So what do we do first? We let y equal negative 2x plus 3. So we're going to subtract 3 from both sides. Y minus 3 equals negative 2x. Divide both sides by negative 2, and we got y minus 3 divided by negative 2 equals x. Now, we're not supposed to have a negative in the denominator, so we'll move it up. So we got negative y plus 3, negative y plus 3 over 2 equals x. And then we switch them around, and we have y equals negative x plus 3 over 2. And all I did was switch the x and the y. So the inverse of f of x, and I'm just replacing this, the y with that symbol, is negative x plus 3 over 2. So let's see, I need to graph that. So let's graph this one here. Let's find 3, do it in red, and then down 2, right 1, down 2, right 1, down 2, right 1, and there we go. And so let's graph that. What do we got here? And it looks like that. And that is f of x. Now what about the inverse of f of x? We'll do that in blue. So let's find 3 halves. That's going to be right there. 3 halves. And we're going to go down 1 and right 2. Down 1 and right 2. Up 1 and left 2. Up 1 and left 2. So let's draw that line. And look where they cross. Again, they both cross on the y equals x line, right there. Modeling with the inverse of a linear function. In a model for a real-world situation, the variables have specific real-world meanings. For example, the distance d in miles traveled in time t in hours at a constant speed of 60 miles per hour is d equals 60t. Writing this in function notation as d of t equals 60t emphasizes that the equation describes distance as a function of time. You can find the inverse function for d equals 60t by solving for the independent variable t in terms of the dependent variable d. This gives the equation t equals d divided by 60. Writing this in function notation, t of d equals d over 60 emphasizes that this equation describes time as a function of distance. Because the meaning of the variables can't be interchanged, you do not switch them at the end as you would switch x and y when working with purely mathematical functions. As you work with real-world models, you may have to restrict the domain and range. For the given function, state the domain of the inverse function using set notation. Then find an equation for the inverse function and graph it. Interpret the meaning of the inverse function. The equation C equals 3.5G gives the cost C in dollars as a function of the number of gallons of gasoline G when the price is $3.50 per gallon. The domain of the function C equals 3.5G is restricted to non-negative numbers to make real-world sense. You can't get a negative gallon of gas. So the range of the function also consists of non-negative numbers. This means that the domain of the inverse function is C such that C is greater than or equal to 0. So I'll let you finish that, and then we'll pick that up here on B. A car's gas tank, which can hold 14 gallons of gas, contains 4 gallons of gas when the driver stops at a gas station to fill the tank. The gas pump dispenses gas at a rate of 5 gallons per minute. The equation G equals 5T plus 4 gives the number of gallons of gasoline G in the tank as a function of the pumping time T in minutes. The range of the function G equals 5T plus 4 is the number of gallons of gas in the tank, which varies from 4 gallons to 14 gallons. So the domain of the inverse function would be G such that 4, the initial, how much was left in, it had 4 gallons of gas in it, so that's the minimum it could be, and it only holds 14 gallons. That was how much it would hold. Solve the given equation for G to find the inverse function. So we've got G equals 5T plus 4. Solve for T. So we're going to subtract 4 from both sides and then divide by 5. So we'll have G minus 4 divided by 5 equals T. So the inverse function is T equals G minus 4 over 5. Now it says graph the function. So we start here at 4, right? That's where we start. And we can only pump in 14 gallons. So if you got 4 and it pumps 5 gallons, let's see, 5 times, let's see here, 1 plus 4, that would give you 5 plus 4, that's going to be 9. And then, so we're going to have 9 at 1 minute, and 5 times 2 plus 4, well, that's going to be 10 plus, that's going to give you 14. So it's only going to take, let's see here, it's only going to take 2 minutes to fill up that gas tank. So let's draw that. Let's draw that line. So here it is. Now with that, you can, at any time, you can determine how much gas is in the tank. So we graph the function. What's next? The inverse function gives the pumping time in minutes as a function of the amount of gas in the tank in gallons. Your turn. For the given function, determine the domain of the inverse relation. Then find an equation for the inverse function and graph it. Interpret the meaning of the inverse function. A municipal swimming pool contains 60,000 gallons of water. A municipal swimming pool containing 600,000 gallons of water is drained. the amount of water W in thousands of gallons remaining in the pool at time t in hours after draining begins is W equals 600 minus 20t. All right. So let's see here. Determine the domain of the inverse function. Well, let's see. The range of this is going to be the range W such that 0 is less than or equal to W, which is less than or equal to 600,000 gallons. All right, that's going to be the range. This will also be, that's the range of f of x, and it'll also be the function, or it'll be the domain of the inverse function. So this is going to be the domain of the inverse function. 0 to 600. Next, we want to solve the given equation for t to find the inverse function. So we have W equals 600 minus 20t. So we're gonna subtract 600 from both sides. So we got W minus 600 equals negative 20t. Then we're going to divide both sides by negative 20, and we have W minus 600 over negative 20 equals t. Now we can't leave it down here, so we're going to put that up there, make that positive, and get rid of that. So to write it, t equals negative 1 over 20 W plus 30. Now let's graph that. So let's find 30 on here. 30. And we know there was 600 gallons, so there we go. And then we'll draw our line. There we go. The inverse function gives the time in hours the pool has been draining as a function of the amount of water in thousands of gallons remaining in the pool. So the inverse function gives the time in hours the pool has been draining as a function of the amount of water in thousands of gallons remaining in the pool. Good. Elaborate. What must be true about a function for its inverse to be a function? The function must be 1 to 1. Eight. A function rule indicates the operations to perform on an input to produce an output. What is the relationship between these operations and the operations indicated by the inverse function. The inverse function undoes the operations of the original function. The inverse function undoes the operations of the original function it performs the inverse operation of each original operation and in reverse order. How can you use composition to verify the two functions f of x and g of x are inverse operations? Well, if f of g of x equals x and g of f of x equals x, then f of x and g of x are inverse functions. Describe a real-world situation modeled by a linear function for which it makes sense to find an inverse function. Give an example of how the inverse function might be useful. Grapes are $1.80 a pound at the grocery store. So the equation C equals 1.8 G gives the cost C. Well, let's use W. Gives the cost C in dollars for grapes with a weight W in pounds. In dollars. In pounds. All right. The inverse function is, that would be W equals C divided by 1.8. It gives the weight of the grapes purchased as a function of their cost. You could also use the inverse, for example, to find the weight of the grapes you could buy for $5. Essential question. What is an inverse relation? What is an inverse relation? It is a relation that reverses all the pairings of some other relation. It is a relation that reverses all the pairings of some other relation. If a relation pairs an input x with an output y, then the inverse relation pairs the input y with an output x. In other words, yx would become, or xy would become yx. There you go. Great job, folks. See you tomorrow in class, and enjoy.